This is part 6 of the Chapter 2 summary for the Deep Learning book authored by Ian Goodfellow and others as presented on screen here. This video is actually an addendum to the videos that came before. In this video, I'm taking a detour from the contents of the text to take a deeper look into principal component analysis, or PCA. I'm doing this because I really felt like there was still more for me to learn before moving on, and I had a few unknowns about it that were pestering me. In the last video, we saw an example of how PCA could be used as a dimensionality reduction technique to compress data, but there were a lot of similarities between the method and what was previously seen in my video on singular value decomposition. The purpose of this video is to further explore what PCA is, so as to bridge the gap between the two in our mental model, and also to clarify something that was critical to both proofs, which is that the eigenvector D with the largest eigenvalue yields an optimal solution to the problem. I wasn't sure about how that was the case, and so I wanted to go through the proof. So, PCA is a term that describes the several procedures related to the construction and usage of principal components, which are defined as the unique collection of orthogonal and thus unrelated vectors, which make up an alternative and smaller dimensional basis for a given data space. There are multiple ways to go about determining what these vectors are, and so these different methods are what PCA encapsulates. As I mentioned, I want to build a bridge between what was seen previously, so I'm going to limit the perspective here to the form of principal component analysis seen in the last video, and to the singular value decomposition seen in a previous video. But you should be aware that there are other methodologies for carrying out principal component analysis. I'm limiting my analysis to these two methods because the singular value decomposition is mathematically proven to be able to provide the best possible approximation that can be made for a matrix for a given rank. So the mental model I'm trying to present here is as follows. There's a basic general form we can follow to put into practice the idea of reducing dimensionality of data, to compress data, or simply to identify principal components. And that form can be arrived at from two different angles. And secondly, in this mental model, this PCA method, is taken further in the form of the singular value decomposition, which, so far as I understand, we can consider as the primary matrix factorization tool for our purposes. If the mental model I've just laid out proves to be faulty in the future, I'll mention that in a follow-up video as I learn and work through the book. So, as I had mentioned at the end of the last slide, the question is, how do we determine the new lower dimensional basis for our data? What I want to present now is two different motivational pathways that lead to the same result for the generic method, which I mentioned first in the mental model. And secondly, I'll take a look at how it is that the SVD can be understood to take these two methods further. So, as I mentioned, two different motivations can be used to define the new basis, to define what the principal components will be in a given principal component analysis. These two different motivations both end up yielding the same computation in the end. We saw the error minimization motive in the last video on PCA. I went through the entire proof presented in the text for how that works. The second of the motivations is the idea, that the minimum data is lost if we aim to select a lower dimensional basis that encapsulates the maximum variation possible in the data. Alright, so what I want to show here is how these two different motivations can intuitively be understood to be equivalent in their outcome. We can see this by looking at the triangles formed when data is projected. This example is about reducing two dimensions to one dimension, but once it makes sense to you, I would really encourage you to visualize or sketch out how this would work if you were compressing 3 dimensions onto 2. So we can imagine projecting a bunch of data points in a two-dimensional plane onto a straight line, and that's what we see here. As we've discussed in the past, what we're fundamentally doing is compressing one dimension out of the picture entirely. This projection is a kind of compression, which inevitably throws away some data. So to solidify this idea, and you can see it in real life, you can use these images to see how projection can really change information that's present. The images show an art installation, where objects are hung at seemingly random points in space, but create a meaningful image when projected onto one 2D plane, which is what we see from a certain angle. We see an image as if it were projected onto a single 2D plane. So in the case of the art, the projection onto the 2D plane made the image sensible, but actually, if you were tasked with stating where each constituent object was in space, while only being able to take that cleaner view of the image, you wouldn't be able to give that information accurately, the information as to each object's depth. So this gives you a sense of how data is lost by projecting onto 2D. Again, we want to see how minimizing error and maximizing variance are equivalent. So to see this, we can start by looking at how we would compute each of these. Since we're compressing onto one dimension, we can think of it as a number line. So measuring variance of the projected points is straightforward. It boils down to a measure of the distance between each projected point and the overall average. So we can see that the greater the angle between our basis vector and our data vector, the smaller the distance between the points. It's clear to see in the case of only two data points being connected, which is shown at the top of the slide. The longest side of the triangle is the hypotenuse, and so maximizing the variance of our data set means having the basis be on that line, so as to have the maximum difference between points when projected onto the basis. And if the basis is the hypotenuse, then it passes through both points, and so the error is 0. Building on this, it should be pretty clear that the maximum possible variance we could have would result if all our points happen to fall across one dimension, and we selected that as our basis. Of course, that's idealistic, and the points don't line up, so that's why our compression is imperfect in the first place. Nonetheless, hopefully this shows how, by seeking to maximize variance, we can find the best case scenario, a line of best fit, and that's going to be the same one that we would get when we try to minimize the error. These two modes have the same behavior. The larger the angle between the basis vector and the data vector, the larger the error vector, and the more compressed the projection is. Therefore, the smaller the variance. And the smaller the angle between the data and the basis, the greater the variance in the projection and the smaller the error vector. So I hope that this makes the intuition clear for why the two motivations, maximizing variance versus minimizing error, actually yield the same data outcome. Now I'm going to get into the math, and my goal is to clarify the proof that the eigenvectors are the optimal solutions for our reduced basis, since I didn't want to leave this fact as a seemingly deus ex machina axiom. So in my last video, I went through the math for the minimizing error technique. So I'm only going to do a step-by-step look at the math for the maximal variance strategy in this video. Naturally, we should review what the definition of the variance is. I find it best to understand variance of a variable as the special case of the covariance with itself. So the covariance is the expected value from multiplying the deviation of two variables from their respective means, and variance is what you get when you perform this for the same variable against itself. As I had mentioned in the example, it was easy to compute the variance in one dimension because it was just a number line. But we need to keep in mind how these ideas apply to higher dimensional vector space. So I'm going to go through the math here that would apply to whatever dimensional vector space you might have. So transforming the variance formula into the vector space looks like what we see on the right. First of all, the mean of the data set can be simply taken as the mean of each data vector. So straightforward vector addition and scalar division applies. The computation of variance of a multidimensional data set along a single selected basis vector u is then relatively straightforward. As seen visually in the example prior, the basis vector acts as a number line. So we get scalar data points by projecting our multidimensional data points and the mean data point onto the basis. Once we have those scalars, we can straightforwardly compute the variance, as we typically would. So that's encapsulated, projection and all, in this equation on the right. The problem is that this summation notation is really clumsy, and this formulation doesn't lend itself to the application of other mathematical tools that would allow us to optimize. So instead, we can go about it another way. Instead of computing the projected data points, and then looking at the variance of those one-dimensional values, we can reverse the process. By that I mean we can first compute the covariance between all dimensions, and then we can project that aggregated information about the variance onto whatever new dimension we wish to define. It would be a more generalized approach, which allows us to optimize. This can be done by spreading computation of variance across many matrices and summing them. What we're doing here really is constructing the covariance matrix, a pretty classic tool. Since covariance is the expected value of the product of the deviation of two variables, we can accomplish this by taking the sum of the covariance matrices created by each data point. Here's what I mean. Each data point encapsulates one data value for each dimension. So a vector might be x, y, and z, 3 values. And each of these values for the different dimensions can be compared against one another for each data point. So a covariance matrix can be created for each data point, and then they can all be averaged to create the covariance matrix for the whole data set. A matrix offers a clean way to present this computation. So by collecting this matrix for all data points and then dividing the number of data points, we naturally carry out the process of computing the covariance matrix. Think about it. We compute the expected value by summing all relevant items and dividing by their count. And in this case, each item is a matrix containing the product of the deviation of the data points. So with the covariance matrix in hand, we can project this variance information onto the axis of interest. So, as mentioned previously, we can project the total variance in the data onto any given dimension with this equation. And what's key for us is to be able to optimize it. And that's much more feasible since we can differentiate this formulation with respect to the vector u. We couldn't do that before with the summation formulation. So by multiplying our basis vector on the right with our covariance matrix on its left, we create a new vector that's no longer a unit vector, and which we can describe as like our original basis, but stretched into each dimension to the degree that our data has high variance in that direction. I recommend just listening to that statement once more if it didn't make sense. We can actually see this empirically, but I'll show a mathematical proof later on as well. So let me show this empirically. What we see over here in this visualization is a few things. First of all, there's a data set, and these are the red points. So it's a three-dimensional data set, and you could think about it as students' grades. So there's 3 courses, so we could say the x-axis is English, and the y-axis is mathematics, and the z-axis is art. These 3 different scores. And then so each point represents 1 student and their scores. Then we have a few other points. The purple point close to the origin represents a unit vector in a random arbitrarily selected direction. The other purple point up here at the top of this arc represents the result of transforming this unit vector purple with the covariance matrix. So we had this unit vector purple as a vector, and multiply it by the covariance matrix, and it yields this purple point over here. To get the remaining arcs, the remaining points in this arc opposite the data cluster, I took the point transformed with the covariance matrix, the purple point, and I looked at its direction, and I created a unit vector for that direction. And then I transformed that unit vector once again, and that yielded this blue point. Then I got the unit vector for that direction, transformed it again with the covariance matrix, yielded the yellow point, etc. So this iterative process of continually transforming with the covariance matrix created this arc. Now, what's happening, there's a couple of things to note. Every time it transforms, the direction changes in this expected way. I mean, it's heading the same direction. It's always heading down like this. And where that's heading is to an axis that's cutting right through the center of the data cluster. If you orient yourself like this and look right through the center of the data cluster, the red dots, you can see that those points at the bottom of the arc line up with generally in the center of the data cluster. You can look at it from this direction as well. Secondly, you can notice that there are diminishing returns on these changes. What I mean by that is that the distance between these points actually kind of shrinks over time. So these ones are at the tail end of the arc are closer together than some of the ones that were midway through when they were transformed. So what's happening here is you can see that the variance of the data is largest in this direction, in this vector cutting through from the origin, cutting through the middle of the data cluster. That's where the most variance is present. And when we take a unit vector and incrementally, iteratively transform it by the covariance matrix, we find that it yields a vector that tends to be stretched towards that axis of maximal variance. And so that's what I was describing earlier. The 2 green points on this positive space are also another example of this. So this green point over here is an arbitrarily selected unit vector, just coming off of the origin. And you can see how, if we take this top-down view, you can see how this second point, which is that unit vector transformed with the covariance matrix, is actually pointing more at like a 45-degree angle from the origin through the xy plane. You can see if you extend an arrow in the direction of this green dot, it's passing way to the side of this second green dot. So that shows how it's been stretched towards the center of the data cluster. And there's actually a link in the description. You can open this 3D plot for yourself and change the orientation, take a look, and do that as you'd like. So, to ground us once again, I'll remind you that the objective was to select a basis so as to maximize the total variance. And right now, we have what you might call a variance synergy vector. And that's the transformation of a unit vector with the covariance matrix. We also know that the closer the data synergy vector is to the basis vector, the closer that basis is to the data cluster center axis vector. Again, that's just what I reviewed in the past couple minutes. These two characteristics create a situation where the projection of the synergy vector onto the basis vector is actually greater the closer the basis vector is to matching the direction of the data cluster central axis that captures the most variance. So that's why projecting the synergy vector onto the basis that yielded it provides a measure of how much variance is captured by a given basis. So that's the rationale behind this formulation, U transpose our basis by S by U. So S by U creates a variance synergy vector, the transform. And then UT by that projects that synergy vector onto the original basis vector. So the greater the change in direction, the further away that basis was from the principal component of this data set, this variance central axis. And thus, the greater the direction change, the smaller the projection will be. So by maximizing this formulation, we have a scenario where we can maximize the variance of our that's captured by this basis we select, U vector. So that's an expression that we can maximize. The problem with the current formulation is that the math points us to making our basis an infinite vector so as to maximize the expression. To prevent this, we have to explicitly add the constraint at this point that the basis must be a unit vector. Maximizing a function is made more complicated though when we add constraints, especially for a vector function such as we have here. Here's why. Normally, to find a critical point of a multidimensional function, you would apply the gradient function to it and then solve for it being equal to 0. That's because the gradient function serves as a kind of way of computing the derivative for a multidimensional scalar function. The reason there's a roadblock in our situation is that we're imposing an outside constraint. So if we analytically solve for where the derivative is equal to 0, we might find many local maximums and not know which one is inside our constraint space. Alternatively, we might even find that there's no global maximum at all, such as if the function creates an upward turned bowl shape, such as is called a paraboloid. In such a scenario, a maximum would have to exist in the subspace we constrain, ourselves too. But the math we have right now couldn't get it for us, even though we're certain that it would exist. Luckily, we have a mathematical tool to solve this problem. So now we introduce what's called the Lagrange multiplier. So I won't go into all the fundamentals and theory behind it, but I do want to step aside for a moment to explain it. The idea is that we can express the constraint we have as a function that's equal to 0 when the constraint is met. Then, by adding that function to our equation and multiplying it by a new variable, we create a useful situation. The situation is that when we take the gradient of our function, we will inevitably take the partial derivative with respect to the Lagrangian multiplier, that scalar we introduced. And since our constraint is the only element of the function that has this multiplier, this constraint is all that remains after taking the partial derivative. In this way, we create for ourselves a system of equations which yield our desired optimal points. And we know the optimal points we find will meet our constraint because the constraint is present in the system of equations yielding those points. So with this idea in mind, we can move forward. Also just note that the Lagrangian multiplier can take on multiple distinct values. And if it does take on multiple values, each one is associated with a unique solution equally viable to the maximization or optimization problem. So there could be multiple solutions with the same value. And it's most often the case that the multiple Lagrangian values will be found that satisfy the system of equations, and these correspond to different critical points in our solution space, which have to be tested on being the maximum or minimum. It's important to note that that gives the critical point, but it does not guarantee whether it's a max or a minimum. So we ended up with this Lagrangian expression that contained our function and Lagrangian addition. And after deriving with respect to the basis vector, since that's our variable to solve for, we end up with this function. We have the covariance matrix S times U, and that's going to be equal to our Lagrangian, some constant value, times U. And this is our magic moment of realization. What this equation states is that the vector which maximizes the variance of the data projected onto it is the vector that, when transformed by the covariance matrix, is scaled up only by some scalar value. And of course, if you're following along, you probably realize that this is in fact the definition of the eigenvector. So only eigenvectors of the correlation matrix, or covariance matrix rather, could fulfill this criteria of linearly scaling up after transformation with the matrix. Again, we wanted to maximize this function, so we set the derivative equal to 0. And that set up this equality for us, which can only be true when our chosen vector is an eigenvector of the covariance matrix. Going back to the original equation we wanted to maximize, we know that it will be equal to the eigenvalue when an eigenvector is used to evaluate it. Since our objective function was to maximize this function, it's obvious that we want to maximize, or that we can maximize our function by selecting the eigenvector of the covariance matrix associated with the highest eigenvalue. It's literally just, you're free to pick and choose because any eigenvector will satisfy this equation, and each one has a different eigenvalue associated with it. And so we pick the one that has the largest eigenvalue to maximize, to optimize our scenario. If you recall, we started our proof by defining our transformation matrix D to be just one column vector. So we were saying we were reducing our, we were only selecting one principal component. We're reducing our matrix to rank 1. But it can be a larger matrix so as to capture more data and more variance. And to make the larger matrix, you only have to sequentially add on the eigenvectors with the next highest eigenvalues to the transformation matrix. And also, in case it isn't clear, these eigenvectors are actually what we would call the principal components. Something that should be kept in mind is that because a covariance matrix is guaranteed to be symmetric, its eigenvectors are guaranteed to be orthogonal. And that's a property of symmetric matrices. This is really important because having principal components be orthogonal means that they have no covariance with one another, and they're totally independent of one another. Now I want to quickly return to the visual we looked at earlier regarding the covariance matrix stretching vectors in the dimension of the axis of the data cluster. So this behavior now totally makes sense. This behavior wherein iteratively transforming the vector by the covariance matrix had it stretched towards this principal axis of the data cluster. And we can see that, we can imagine that with this eigendecomposition on the right. Each time a vector was transformed, its constituent eigenvectors would be stretched by their eigenvalues. Based on this, it makes sense that the vector would stretch in the direction of the nearest, strongest eigenvector. By strongest, I mean the one with the greatest eigenvalue. That's because every time it was transformed, each eigenvector would have its contribution to the original vector, that is, the manner in which it contributed to it as it decomposed into those eigenvectors, would have that contribution multiplied by its eigenvalue, almost like a weight. So doing this iteratively would have all but one eigenvector continuously lose weight with respect to the total contribution to the resulting vector. And that pattern would proceed with the resulting transformed vector more and more closely resembling the eigenvector. So we can see that on the right here, how if we imagine that this green eigenvector direction has an eigenvalue of say 1.5, and this red eigendirection has an eigenvalue of, say, 5. After transforming our arbitrarily selected basis, that's yellow, with the covariance matrix, you could look at the decomposition to carry out that transformation. The red vector gets stretched by 5, the green vectors get stretched by 1.5, and you can see that it's only natural that the yellow vector would appear to be stretched towards the principal axis with the eigenvalue of 5. So as I noted here on the bottom, as you repeat this iteration, the angle approaches 0 between the two. So once we know this, no iteration is necessary. That just makes for an interesting visual. We know that if we want to maximize the projection of our variance synergy vector onto our basis, we should choose the vector going through the axis of the data variance, the direction that our iterations always stretch towards. And that's because if our vector is right in line with that, the synergy vector is exclusively and entirely stretched by the largest possible eigenvalue, as opposed to being, for example, 60% stretched by the largest eigenvalue and 20% stretched by the second largest, and so on. In addition to that obvious strategy, the fact of exclusively linear scaling also maximizes the value of the subsequent projection. So it's simply the case that no vector could offer a more optimal solution than the eigenvectors in decreasing order of eigenvalues. Alright, so at this point, I want to zoom out and take a look at the big picture again. First, I intuitively showed the reason that minimizing error due to projection and maximizing data variance after projection yield the same solutions. Then I showed the mathematical process for selecting the basis vector that provides maximal data variance. And I just finished showing intuitively why it is that it's only natural that the eigenvectors would provide the optimal solution. As I laid out in the roadmap for this video, what I want to do now is show another rationalization for why the eigenvectors are also the optimal solution with respect to the error minimization method. I'm doing this because in the process of creating the previous videos, I really wasn't satisfied with accepting the axioms that eigenvectors would maximize the expression we had. I wanted to understand that more completely. So I'm not going to go over the entire mathematical proof again for how the minimizing compression error strategy allows us to choose an optimal basis, as that was in my last video. But I do want to review yet another different proof for why eigenvectors of the covariance matrix are the optimal basis. Because in the last video where I reviewed the proof, I just left the fact of eigenoptimality as an axiom. So let's jump to that last step from the proof. Oops. In the process of trying to minimize data error, we arrive at the objective function of maximizing the trace of the expression of x transpose by x bracketed by d transpose and d. So this is where the magic happened, and we simply said an eigenvector was going to be optimal. Now I want to break that apart and show why that is in a more symbolic mathematical way rather than the very visual and intuitive proof I just showed earlier. So we'll get both sides of the coin here. So this is a kind of more pure mathematical approach, and it's meant to reinforce that visual intuition, whichever one you prefer. First of all, we know that the xt by x, which we see in the middle, will necessarily create a new symmetric matrix. So we know that this matrix, if we call it A, will have positive or zero valued eigenvectors or eigenvalues, and all of its eigenvectors will be orthogonal to each other. And that's just because it's symmetric. That's a property of symmetric matrices. So next we can consider the matrix A as equal to its eigendecomposition. So our equation gets re-expressed by substitution of the eigendecomposition in for the matrix. Now what I'll do is look at this mathematical process, this big jumble of matrix multiplication, step by step, and you'll see it's eminently clear that the eigenvalues and vectors are necessarily the ones that maximize the result, thus the ones we're seeking. First, we'll start at the right. Work right to left of this expression. We're multiplying our unknown unit basis vector by the transpose of the eigenvector matrix. What's this really doing? First of all, the matrix is orthogonal. So the transpose is actually the same as the inverse. And I'm referring to the eigenvector matrix. What this is really doing then is it's performing a change of basis. It's translating our basis vector, which we're looking for the best one, from our basis, x, y, z, or whatever, that language of that coordinate axis, into the basis where the eigenvectors define our coordinate axes. So mathematically, the outcome is a matrix that would look something like what we see here on step 1. And note that I'm only showing the diagonal entries on the right side there because our function is inside the trace operator. And so we're only concerned with maximizing the diagonal. So the question immediately becomes, what basis vectors, organized into a matrix, would maximize our trace right now? And we can see the trace is made up of the projections of our basis vectors onto the eigenvectors of that matrix xt by t, or by x rather. So knowing that both of these vectors are unit size, it's obvious that the dot product could only be a maximum of 1. And that would occur when these vectors are collinear, or to be clear, the same. Okay, so right off the bat, step 1, we're performing one little computation here out of these multiple computations in sequence. We can already see that the eigenvectors are the ones that would optimize our scenario. So let's continue working through the math. The second operation is the multiplication of the matrix we have with the diagonal eigenvalue matrix. This operation is super simple. Again, I'm only looking at the diagonal since the trace operator is what's in question here. Because of the nature of the diagonal matrix, each diagonal element is just multiplied by the associated scalar eigenvalue. Our choice of basis has no impact on the operation since it's just scalar multiplication of these terms. So the optimum answer is the same as before, that our basis be equal to our eigenvectors. Nothing's changed really because it's just scalar multiplication. To make sense of the next bit, step 3, we'll look at the two final operations together. The first is multiplication with the eigenvector matrix, as they are expressed in standard coordinate axis language. So essentially, this is a change of basis again, from the eigenbasis to the standard basis. The last operation looks like matrix multiplication, but really once again, it's taking the dot product with the basis vectors we chose to construct the D matrix, much like step 1. And again, because we're looking at the trace, all we're interested in is the diagonal, which is going to be the vector we've developed so far, projected back onto the original bases. The first part, multiplying by v, is a change of basis. If we look at the numbers, it's not really clear how to make any intuitive sense out of it. Changing a basis can have unpredictable effects on the actual numbers in a matrix, though we know that a basis is just a language to describe a vector, and changing the basis doesn't affect the size or direction of the actual vector we're talking about. It just changes how we refer to it. So since the numerical output of that change is not predictable with respect to the numbers we'll be adding in the trace, instead of chasing those numbers to look for optimality here, we'll look at the intuition and go to the fourth step, projection back onto the basis. Since our basis vector is a unit vector, then no matter the length of the vector we're projecting, the dot product will always be maximized if the vectors are collinear. So to follow the cookie crumb trail here and to chase the optimal maximized solution, we're seeking a vector that, after being transformed by our matrix A, will be collinear with its original version. Once again, the only vector that fits this bill is the eigenvector. In fact, that just bears out from the definition of the eigenvector, that only its scale and not its direction are changed by transformation with A. And the way that this bears out actually applies to every basis vector that we chose. So this is the mathematical proof that for this error minimization approach, as well as the variance maximization approach, the eigenvectors of the matrix formed by the data correlation form the optimal basis for principal component analysis. Alright, so what we've done so far is show how the minimal error and maximum data variance approaches are essentially equivalent in their outcome. And we've seen both intuitively through visualization and evidently through mathematical analysis that in both approaches, eigenvectors of a covariance or correlation matrix, which is created from the initial data matrix, provide the optimal solutions. What I want to do now is tie this all together with the singular value decomposition to wrap up this discussion of principal component analysis in general. First of all, in my video on the SVD, I hadn't yet encountered principal component analysis, so I can now clarify how they relate. Singular value decomposition is fundamentally a process you can perform mathematically to create an approximation for a matrix. On the other hand, principal component analysis refers to a data science technique. Do you see a difference? PCA is all about data, where the SVD doesn't care if a given matrix represents a collection of data or just a linear transformation or anything else. The distinction is that the SVD is just a mathematical method, where PCA semantically entails the central motivation of breaking data into an alternative basis. Of course, the key thing is that the SVD method can be used as a means of performing principal component analysis. And the reason for that is that the SVD offers the principal components on a silver platter. It's important to identify these correctly though, as where you get the principal components themselves depends on the design of the data matrix with respect to the SVD. In my video on the SVD, I refer to the columns of the U matrix, the left singular vectors, as building blocks. In PCA terminology, these would be the principal components. The critical thing to keep in mind is that that was the case because the matrix was organized such that the columns represented data coordinates for independent variables, and the rows were the data values for the dependent variables. If, for whatever reason, data in a matrix is stored row-wise, then the right singular vectors would be the principal components. If that's the situation, you just need to make sure not to get mixed up with the transpose. The singular vectors of the V matrix are the columns before transposing, or its rows if the transpose is evaluated. I'm also sharing a link in the description to a document from Stanford containing some really interesting interpretations of not only the principal components of the SVD, but the ways that the singular vectors left or right that aren't principal components can also be interpreted. Alright, so since I already discussed the SVD motivation and mathematics in detail in a previous video, what I want to do now is provide a purely visual mental model for intuiting that the SVD provides the best low-rank matrix approximation. To be specific, the Eckert-Young-Mirsky theorem states that the SVD is the best possible way to create a lower-rank matrix approximation, insofar as it minimizes the Frobenius norm of the error matrix between the original and the approximation. This can be understood through the lens of how the SVD maximizes the variance of the data that's captured. Again, this understanding is just meant to provide a visual, and I'm not making any claims about how mathematically robust it is. So consider this. When we developed the principal component analysis on the basis of maximizing data variance, we computed the variance between data points. Visually, that means we computed the variance between columns in our matrix. But the fact is, you can objectively say that some relationship exists between all numbers in a matrix. To get the best possible approximation matrix, it would only make sense that we would want our approximation to encapsulate the patterns and relationships across rows of the matrix as well as across the columns. So this is the great strength of the SVD, and we can imagine it visually as follows. So let me cut to a draw pad over here. So let's say we have a small table, data table, with these three companies, and the market cap and last year's growth rate for each company. We can compute the variance of this data and proceed to try and create a low-rank approximation. But what if we did that? If we did that, we'd be ignoring the latent data in the rows. What I mean is the following. With our variance calculation as we described it earlier, we have some data matrix, and we observe some data here. And what we did before was essentially just taking the covariance of this. There's a covariance matrix there. So there's kind of like a sigma 1 squared, a sigma 2 squared, and then a sigma 1, sigma 2, sigma 1, sigma 2. And then we looked at the variance for this column right over here. And that created another one, another covariance matrix. Sigma 1 squared, sigma 2 squared, and then sigma 1, sigma 2. And this is symmetrical. And then we took the average of these two. So we put them together, and we had an overall covariance matrix. And what I was just mentioning a minute ago was that what we didn't do is we didn't consider the potentially latent data relationships in these rows, in these relationships, in these data items. The fact is, like I mentioned a minute ago, wouldn't it make sense to make our approximation as accurate as possible to also capture the information, the relationships present between these variables? So that's what the SVD is going to do. So let's say we have this data table. We have companies here, just some fake little numbers to work with. So we have two measures. For these independent variables, there's three companies. So these are two-dimensional vectors. So we have two axes, measures, growth, market cap, and it's two-dimensional vectors, so each is represented by a point in space. Pretty simple. And on the right side over here, we can see the matrices. So what happens when you take the transpose? When you take the transpose, the columns become the rows. And so it all flips around, and we end up with, instead of 3 points on 2 dimensions, we end up with 2 points on 3 dimensions. And so it's a little unfortunate. The angle I drew this at has this growth vector kind of coming out of the screen towards us, so it's kind of hard to see, but you can see the grid here where these coordinates are at. And so this is a lot harder to understand intuitively. It's not a format we would ever normally look at, because we consider the companies as the independent variables and these measures as the dependent variables. But in this axis formulation, we have companies as dependent variables and this vector essentially storing the data of each company on a given measure. So how do we capture this? Or what's really going on here? I'd like to present it a different way. You could understand that this is what we would call the row space. If we look at this vector, this matrix over here, we have 3 vectors in the columns. And those are these 3 vectors over here. So that's the column space. So when we look at this space, what this is that we're considering what was originally the row as a vector itself. 5A4, 734, that's what we're seeing here, 5A4, 734. So this represents a row space of the same matrix. So we're talking about different spaces, and you could understand what I mean by different spaces by looking at these visualizations, looking at these coordinate axes. But the question then is a function on one axis, say y equals x squared, is it the same thing as that function on the other space as well? Is a point in one of these spaces even the same as a point at the same coordinates in the other space? I would say the answer is no, intuitively, because I would think of the axes as being a kind of unit, and those can't be mixed. So for example, if you have some quantity in meters, let's say you have 5 meters, and you have something in seconds, let's say 10 seconds, you can't add these 5 meters plus 10 seconds. This does not boil down into some single value because they're inconsistent units. So, that's why I would say these are 2 completely different spaces. They can't really be related to one another. The big idea here, though, or the question is, why is this useful to us? Well, we said we wanted to maximize the data variance of our approximation. But we see here that data actually exists in 2 distinct spaces. This is data just as much as this is data. I mean, it exists. It's there for the taking. But in our other formulation, we just didn't consider it at all. We only considered this data and how to maximize the variance there. So the big idea is that we could choose a basis vector that captures more variance in total by capturing the variance in the row space data as well as the column space data, where before we might have been capturing very little. So now to visualize this, I want to jump to a 3D plot over here. So I'm just going to change tab right here. Here's a 3D plot of this data. So again, we're looking at the same coordinate axes. I mean, there's just 3 axes in space right here. But you need to consider this as being a superposition of different vector spaces. Because like we just mentioned a minute ago, these coordinate axes have different units. They're fundamentally different vector spaces, and so they can't really be considered the same. So, okay, we have a superposition as if we just put this chart right on top of this one, and we saw all of these points in 3D space. So we have this 2D plane, which is yellow, And we have our 3 data points there, Google, Tesla, Apple. And then we have this, in 3D space, we have these 2 points out here floating around. And that's our market cap data point and our growth data point. So naturally, there's some optimal basis vector for the row space, which we never looked at before. And that will maximize the variance captured in that space. And you could solve for that by the same procedure as we've discussed as solving for the optimal basis vector for the column space. So naturally, this should lead us to the idea that somehow we can mix these vectors into one to try and get the best of both worlds, to try and capture as much variance as possible. So let's take a look at what that looks like. This is actually what the SVD does. This is the intuition that I'm suggesting. The 2 spaces that we're looking at, they're going to be of different dimensions unless the original matrix that we're decomposing was square. So we can visualize the new strategy as being selecting some basis vector in the higher dimensional data space that captures some variance there. And in addition to that, the same vector, because we're only choosing one basis at a time, right? That same basis vector would capture more variance when projected into the lower dimensional space. So we can visualize this using the mock data set. All right, so let me just sketch out this mock data set over here on my draw pad. So we have, an axis cutting through, and I'll do it kind of generally, just kind of roughly. We have an axis, and we have 3 axes, of course. And so we have some points out here in space, and I'll make them green to match that image over there. We have a point out here in space, and so these are coming down here way ahead of this 2D plane. There's this 2D plane, and they're coming out of it. And so this one we can say is over here, and then we have this one, well, let's say it's right over there. We can say it's kind of going in the same general direction. All right, so the idea now is that if we imagine, coming back to this other visualization, we saw how the eigenvector was going to be cutting right through the center of the data cluster, and it's only natural that it would capture the most variance that way. Again, same thing as minimizing the error. It's trying to be as close to all the points as possible. So in this situation, it's only natural that our optimal basis vector for these 2 green points in isolation for this unique data space, our optimal vector would be somewhere, I'll use purple, it would be somewhere cutting through the middle, right? So maybe it would go right over here. So, I'm talking about a point that would come, the head of the point would be right around here between these 2 green ones. And that's our optimal vector there, right? And then similarly, it's pretty clear to see that we have these 3 points in 2-dimensional space. And so the optimal basis vector there, if we had to choose only one dimension, would most likely be, cutting through the middle somewhere around right there, so as to minimize these error vectors. So here's what I mentioned earlier presented visually. What I mentioned earlier was that we have 2 spaces, one in different dimensions, and the idea is that we can choose a higher dimensional basis vector, such as this one. We choose this one, and then this is like the only basis vector we choose, and then it gets projected onto our lower dimensional space. So there's this plane here in two dimensions with the x and y axes. So this is a plane, and on that plane is our points. So here's Tesla, and there's Google. So I'm just redrawing this graph right over here, something like this, you know. So that's just a two-dimensional plane. These just are points in two-dimensional space. And it's almost as if, and again, this is just for visualization, I'm not making any comments on how mathematically robust it is, but we could see that this vector, it's optimal for these green points. And what happens if we project it? Well, if we project it, we're just going to take where it touches on the axis there, and where it touches here, and we'll connect those points onto right here. And if we connect it, then we see that this vector actually cuts through the two-dimensional plane along this direction. So it actually cuts through higher, like up here. You see that? You see it? Here's the x point, y point. So we make this square window on our plane to see where it's going to be going. And so what has this just done? What we're saying is that if we choose this vector as our basis, which is optimal for these green points, then what we're doing is we're capturing as much variance as we can in this data space, this row space. And at the same time, that basis vector, when applied to lower dimensional space, will capture not the optimal amount, because we said this one through the middle was the optimal amount, but it's going to capture some not bad amount of variance. I mean, it's not nearly as bad as a vector that's going there, say, which is totally off axis. So this is the idea. The idea is that we had data in higher dimensional space that we were just ignoring. So if we looked at the green points before, you know, our more basic principal component methods might only look at the column space. So our basis vector would be this purple guy over here in 2 dimensions. And so we'd be missing a lot of the variance of the data in the row space. And so by instead looking to this higher dimensional space to make our basis vector and looking at our lower dimensional space at the same time, we can find a happy medium where the higher dimensional vector will project onto our lower dimensional space so as to maximize the total variance that we capture. And I'll share a fun analogy for this. It's kind of like if you imagine, here you have a plate. Let's say you have a square plate. It's a cafeteria tray. And you're over here, and you're a hungry hippo. So you want to get as much food off your plate as possible. And it's almost as if here we had you know, a bunch of food. Just had a big pile of food here. And here, there was another pile of food. But this was actually invisible to you because it was in a higher dimension. So this is our green data points. And before, you were only operating in 1 dimension. So you would just get a shovel and you would just shovel this whole pathway of food. All this food right here, you just shovel that into your mouth. And that's like the variance that we're capturing. Now, instead, with the singular value decomposition method, you are able to put on your magic goggles and see all this invisible higher dimensional food that you couldn't before. And you're able to move in higher dimensions. So instead of just being able to go in a straight line, now you can say cut across the diagonal and get a whole bunch of food that you never could get before. Or in this case, what we're talking about is capturing as much variance as possible in the data set. So you see how being able to move multidimensionally, being able to work in multiple dimensions, and see and capture more data than you could before would make your matrix approximation better than otherwise. So again, this perspective on the SVD is not necessarily mathematically robust. This whole idea of projection of into higher spaces and back into lower spaces to capture variance, not necessarily mathematically robust, but this is how I'm understanding this intuitively. It makes a lot of sense to me, this idea of there being latent variance in data that's not captured by simpler, more straightforward or lower dimensional methods. So regardless of whether or not you like this analogy, what I would suggest is that the main idea is to realize that there is data hidden in the matrix that isn't captured by the other methods, and that's in the row space, that's in the rows, and that the SVD is able to get at it. So in the case where a matrix was square, then this idea about the SVD's strength wouldn't be about projecting a principal component onto a lower dimensional space, but instead just modifying the vector direction to take into account new data points in that same dimensional space. So if our data matrix was square, this data right here, it wouldn't be on a plane. It would be in a three-dimensional space. There'd be some other space here. And so we would have points spread throughout this 3D space. So then when we looked at this graph over here, then we would have points from both our column and our row space spread around this 3D space. And so when we talk about finding a vector that maximizes the variance for both of those data sets, it would be simply just like looking at all the points at once instead of just looking at group 1 or just looking at group 2, row or column. So that's how this extends, to a square matrix, you might say. So I hope that you found this video helpful in putting a bow on the idea of principal component analysis and getting you very comfortable with the proofs for the optimality of the eigenvectors in the different approaches. Now that I feel very comfortable with my understanding of these methods, I'll be moving on to the next chapter in the deep learning book. So again, hope you found it helpful. Thanks for watching and take care.